Alright, so let's do the second part here. So we're continuing on looking at figuring out either the hydronium ion, or just look at, I guess, the hydronium ion concentration, how to figure out Ka, how to figure out the concentration of a weak acid. Now we're going to do the same thing for a base. So, where I don't think okay, for solutions of ionic hydroxides, we assume that the hydroxide dissociate completely upon dissolving. So that would mean something like sodium hydroxide or barium hydroxide. As soon as you put those in water, they're dissociating into barium 2+ ions and hydroxide ions, right? And sodium hydroxide into sodium and hydroxide ions. Generally, we consider those to be strong bases, but that information is not given on the chart. If the chemical formula does not have, this should be on page 28, it's on 28 9, at the very top, right above example number 5 in your workbook. If the chemical formula does not have hydroxide in it, or it's not a ionic hydroxide, and they're saying it's a base, you have to react it with water in order to produce the hydroxide and whatever ion that is. Because we're taking one of these hydrogens, adding it to here, so I would produce. Okay, so this, so quick example, this would be 10 for 1020. So find the hydroxide ion concentration of a 0.064 solution of barium hydroxide. So barium hydroxide, we assume, is disassociating pretty much at 100%, right? So I have that one-way directional arrow to produce barium and 2 hydroxide ions. If the original concentration is 0.064, to figure out the concentration of the hydroxide ions, what do I need to do? Which is times by 2 over 1. So this would give me 0.128. Right, and that's the concentration of hydroxide ions. If they ask me anything else, I could figure out the POH, the pH, hydronium ion concentration from there. Okay. The strongest acids, like I have just already said, they already contain OH in their formula. Weak bases, which is pretty much what we focus on here, unless we're looking at neutralizations. So weak bases, they have a weaker attraction for protons than those strong bases that already have hydroxide in them. And like I said previously, they require the addition of water to produce hydroxide. These reactions are not quantitative, they're not occurring at 100%, so we have to do some different calculations other than stoichiometry, which is using the ice table and the Kb values in order to figure out and answer these questions.
I was just going to see if you could use supervisor, but it looks like you're teaching.
Yes, I am. Yeah, thank you, though. Appreciate it. And to figure out the Kb value, it would be the exact same here as the Ka. Kb would just now be equal to the hydroxide ion over the, and the, oops, that's not the correct thing. Over the Hb, that would be the original concentration of the base, and the Kw, is equal to the concentration of the hydronium ion times by the hydroxide ion. This is a 1.0 times 10 to the negative 14, if you remember. That value for my water ionization constant is in my book. And if I multiply the hydroxide ion concentration and the hydronium, switch those around together, I would get 1.0. Or I can take the Ka times the Ke, which would give me Kw. Now, in our table, we don't have Kb values, but we need to use them to answer some of these questions here. So we will manipulate the formula to become, I'm just going to write it here, Kb is equal to, if I just divided off Ka, I would have Kw divided by Ka. So if they're ever asking you for your hydroxide ionization constant, or usually what they would just refer to is Kb for that equilibrium, we will have to use this formula. And so I'm kind of at the bottom of this page here. And if you want to grab this table out on page, whatever this is, 8 and 9, we're going to use that here for the next few questions. Kw is always that number from water, right? So this is 1.0 times 10 to the negative 14 over Ka. And the Ka values, these come from the data table. Maybe on a rare occasion they would actually come from something you have to calculate, but generally they come from the data table. Yes, that's the water ionization constant. So calculate the Kb of the nitrite ion. So if I'm trying to figure out Kb, I have to use Kw. Where's my? Can you hear me? Where did I put my thing? Oh, it's way over here. Sorry, friends. Hopefully you heard me. Catch up on your own time. Okay, so now I feel really bad. Sorry. That's what you get for skipping. Anyways, okay, so Kb of the nitrite ion, I need to use the water ionization constant over the Ka. So I go to the nitrite ion, so if I go on my chart, the nitrite ion is NO2 negative, which I would also like, you're either looking at the ion or the acid, it doesn't matter, regardless, your Ka is the same and you can figure out your Kb. So my Ka from this chart is 5.6 times 10 to the negative 4. And when I divide those numbers, my Kb value then becomes 1.7, or 1.8 I guess, because it's to 2 significant digits, times 10 to the negative 11. Lots, and like at least I think on every diploma exam that I've looked at, there's always one of these Kb questions. It's pretty easy, but I think a lot of people just forget the formula. I have that slide twice. Okay, so just kind of look at again another sort of question here. So solid sodium benzenate forms a basic solution. Determine the Kb for the weak base present. So we need to figure out what ion is there. So sodium benzenate is NaC6H5COO. And so this is a basic solution. So when I look at what happens when I put this in water, the first thing that would happen is the sodium and the benzenate ion would disassociate from each other. But we never include sodium in our acid-base reaction because it's not an acid or a base, right? It's just kind of a spectator ion, so we don't include it. I would only be looking at this ion right here. So this is CH6,5COO negative. Would be reacting with water in order to produce those basic properties. It's a weak acid, so we have that equilibrium arrow. So what's happening here is the hydrogen is breaking off of the water to produce a hydroxide. So in this case, the water is an acid because it's getting rid of that proton, and it's donating it to that benzenate ion, which is the base. And so I would be producing C6H5COOH. And I should have my states in all of these. Okay, if I know that, to figure out my Kb, they don't give me any other information, so I would kind of just make the assumption that that Ka must be on the chart. The Kw is the water acid, or the water ionization constant, so 1.0 times 10 to the negative 14, over benzenate, the benzenate ion, so I would go to my chart and look for that ion. So that would be coming from the benzoic acid is the conjugate acid to that ion, which is the base, so it's on just the top of the second page. So 6.3 times 10 to the negative 5. So divide those. My Kb for this is 1.6 times 10. 1.6 times 10 to the negative 10. Just, I guess, extension or review while I'm thinking about it.
That's the moles per liter?
Yes, sorry, yeah.
I
What here is the conjugate, like, what are the conjugate acid base pairs in this? Yeah, so conjugate acid base pair and conjugate acid base pair. Okay, so try this one on your own. Give it a second and see if you can figure it out. Hopefully you figured out that I need a color to write with. Ammonia, which is NH3, is reacting with water. Equilibrium reaction, in this case, again, the hydrogen from water, which is acting as the acid, is being donated to the base of ammonia. So I'm creating my ammonium ion and hydroxide. So to figure out the Kb value, it would just be Kw over Ka. So 1.0 times 10 to the negative 14 is being divided by the nitrate, which is 5.6 times 10 to the negative 10. 5.6 times 10 to the negative 10. And so my Kb value should be bigger than that, right? Should be like negative 4 or 5, yeah, negative 5. So 1.8 times 10 to the negative 5, right? And so my Ka value is very small, which means my Kb value should be a little bit larger, and vice versa would be true. Equilibrium constants like Ka, Kb, Kw are always 2 sig figs. Because we're dealing with such small numbers that after that it's just a kind of a guessing game. Okay, so then I'm going to go back to example 6 to look at another question that deals with figuring out the equilibrium constant. So the one way you can figure out the equilibrium constant, if they're not giving you any sort of information other than what substance is being reacted, is you just take that, look at it in its acidic form, and then divide it, the Ka, by the hydronium ion, the water acid ionization constant. The other way here is to figure out Kb is if you are already given an amount concentration. And so this would be the exact same way that you figure out a Ka. So now in this case, Kb, you have to take the hydroxide ion concentration and whatever that other concentration is and put them in here. And so a student measures a pH of a 0.250 mole per liter solution of ammonia and finds it to have a pH of 11.32. Calculate the Ka value for ammonia from this evidence. And so ammonia, we just look at this reaction. It would look like this. Hydroxide. So my products, to figure out my Kb value, it's my products over my reactants, NH4 positive, and I'm starting with the initial concentration of NH3. I do know the original concentration of ammonia, and I do know the pH, but you have to do a little bit of work here. So if I'm going to jump in, and let's say I create this ice table. And this is NH3, this is NH4, this is OH. the initial concentration of the ammonia solution would be 0.250, and we assume that those products are not they're any significant amount. So then the change here. What we're producing is ammonium and hydroxide ions. The piece of information they give for me to use, though, is that pH is equal to 11.32. If I do this and I go 10 to the negative pH, I'm getting what? The what? Hydronium ion concentration, right? Do I need that here?
No.
So what do I need to do to figure out the hydroxide ion concentration? Right, so the first thing I would do is figure out what the POH is. So I would go 14 minus 11.32, which gives me 2.68. So POH is 2.68. Then I can take that to figure out the hydroxide ion concentration and go 10 to the negative POH, which in this case is at 2.68, which gives me 0.002. And so that would then go in this part of my ice table, and because this is a 1-to-1, these would be both increasing by that same amount, and this one would be decreasing by 0.002.
Why is this trying out for American Idol?
What is going on? Oh, I hate that song too. It's like the worst song ever created. It's so stupid. Oh. Stupidest song in the world. Alright, anyways, let's finish it. So, squared. So I'm just putting those in there, right? It's a 1-to-1 ratio. And now it's like the exact same thing we did for the figure out the Ka value. The initial step that you always kind of have to add here is remembering some stuff from Chem 20, using the pH, POH, 10 to the negative, whatever. So I would divide that by my original, or that equilibrium concentration. So clearly the products are still highly favored here. So people that are watching the video are like, what the hell? If I only knew. Okay, so Kb is 1.76 times 10 to the negative 5 joules per liter. I thought it was like the start of a lockdown drill or something. I was like, this is a real weird way to start a lockdown.
Everyone stay calm.
Yeah.
Maybe it's like someone's birthday.
That is super weird. Okay. So, we have a few questions that I do want to take a look at tomorrow, looking at just kind of, again, like what we would have done first class today is what we'll do tomorrow for the hydroxides, where now you have to work backwards. And so if you're looking in the homework there, homework 9, part 2, do questions, everybody ready? So homework 9, part 2, 1 to 4, 6 and 9. 1 to 4, 6 and 9. Okay?